it's pretty compatible, so we'll do that.
Assez branché,
Does your phone plug into your network? That's nothing to do with you. You're just doing the phone.
I'm just doing the phone on a live stream for the YouTube on my computer.
So from YouTube,
The lost people. That was like the only time we were in the fifth floor though. It was,
oh really?
We special. Oh yeah.
Sorry.
No, go for it.
C'est une autre option.
You guys see the chairs? Where's the chairs in the hallway?
C'est bizarre.
The Irish are.
Oh, that's
Sorry. What do you think of the two of you?
I really like that.
Software has a specifically audio digital signal processing. I was like, oh, that's what I do.
Sinon, je suis envoyé un petit mail.
That's sometimes I like to just trying to solve something so I that's back in the same. That's awesome. Yeah, I found the videos. Oh, good for this one. Yeah, great. Yeah. Oh yeah, that's right. Because you were doing a bunch of stuff, right?
Yeah, I know. Yeah.
I just kind of jumped in here and there. I don't know. I found this chapter pretty interesting. Had a lot of insights, but it's all
1 minute. Take your time.
C'est trop beau, c'est trop bon. Mais du temps à la télécharger comme ça. Si un peu.
Come again?
Do the break.
You can break it if you want to. We usually go straight for it.
Do you straight?
Yeah. I think we're ready.
We're ready?
Yeah. Do you want me to present you? Okay. Okay. Oh, okay. So welcome to the chapter 9. Sorry for a little delay. We're really lucky to have Louis present with us today. He is a wonderful presenter and also a very cool guy and a head of AirBnB lab for AI. So that's something to brag about. He'll tell you more about himself. We also have Christian Szegedy come in later. So like at the very end for Q&A, and that's going to be not so much about the chapter, but about industry. So if you have any questions for him about Google research or about any of his papers, that would be a good time to ask him. Take it away.
Thank you. So I'm going to test the sound, my sound. Can you get me in the back? Can you hear me in the back? Okay, I'll try to project even better, and if you can hear me, if I don't make sense, you wave like crazy. Seriously? Seriously? Go away. No. Sorry. All right.
I'll follow you wherever you stay. Yeah, it doesn't matter.
Okay. All right, so now we're starting for real, and I'll try my projecting voice. So please tell me, I just want a quick thing, a quick survey, like who is an expert and is going to correct me? I'm serious. Who knows this thing and just come here for the, no?
This guy.
Okay.
Like a few people for sure.
Who knows next to nothing about convolutional networks? Okay, I feel better. Good. Okay, so I'll tell you why. I think the book we're going through is a great book, but it's a little dry. I think it lacks intuition, it lacks illustrations, and I like to explain so people actually get something out of it, not just a bunch of equations. So you'll see that I really like to make sure that everybody leaves with something. So that's the first thing. The other thing I have to tell you is convolutional neural networks are better taught by people with a French accent. And the reason, and this is the reason why Elena asked me to come. She really wanted this guy to come and present, but he was busy. So I was sort of 17th on the list, and I said yes. Okay, so that's why I'm here. I hope you understand and forgive the accent, but that's the real reason. So I'm not an expert, so anybody can correct me. I won't feel bad about it. Convolutional neural networks. So let me start with what's wrong with fully connected networks. We love fully connected networks. Everything connects to everything. We have two layers. I make them the same size. They don't have to be. And everything connects to everything, right? So you can learn anything. Oh my God, you can learn anything. And it's true. You can learn a lot. But they're very expensive. N-square connection, N-square weights. If N is 10, it's okay. If N is 100, it might be okay. If N is 1,000,000, like on an image, it's not okay, right? This is my French accent reinforcement. I have a few, more French accent. So aside from being wonderful, fully connected layers tend to be very expensive, right? So they take a lot of space to represent and a lot of time to compute. And so when you try to throw them on very large input, like images or videos, it's really painful. So people are being looking for a solution. And in fact, back in the old days, before we had GPUs and things in the cloud, they already came up a long time ago with a solution which was called convolutional network. So what is a convolutional network? I'll try to simplify. It's something where instead of everything affecting everything, a little bit, a limited, and it's called a kernel, a limited little bit of the input affects each output. Right? So, and just to jump ahead, if we deal with things like images, clearly locality is important. So things around a point are much more important than things on the other side of the planet. Right? Not in the full sense of generality and so on, but roughly, the way we see, the way objects, the world is organized, locality is very, very important, and those networks, they respect that. So, okay, so that's one definition. In terms of cost, if your kernel has size k, then suddenly you only need n times k weights and n times k multiplications, which is a lot cheaper. If n was 1,000,000, you got yourself on the order of 1,000,000 kind of saving, assuming k is a fairly small number. Right, so it's a lot more efficient, both in storage and in computation. Now those networks, they have some other properties, and I'll go through them and I'll explain, I'll show you illustrations. So one is called a sparse connection, so this is it. This is the fact that it's limited in terms of connectivity. The second is the idea of parameter sharing, I'll go through that. And the third one is the fact that translation variance means if I take an image and I move it a little bit, basically I get the same result moved a little bit. Right? And that's an important property because often we care about what's in the image, not so much where it is in the image. Right? If I take a picture of somebody and then I move it a little bit to the left, it doesn't really matter. It's the same person. I want to get the same kind of answer. Right? So this is an important property that those networks have, which fully connected networks, they don't really have that. I mean, you can take the pixel and scramble them, and they will give you the same result, which is a very good observation I found in the book. I never thought of it this way, but it's true. You could take the exact same set of pixels and totally scramble them, and they're fine. They recognize the same thing. It's not what you want. All right, what can you apply those networks to? The answer is anything that fits on a grid. So grids, and I'm stealing this straight from the book, 1D things like an audio waveforms. Right? So you got a series of numbers saying how loud it is at this instant and over time, and that the grid being the time series, like every fraction of a second you get a new value. So that's one type. Any sort of time series. This one I wouldn't have thought of. Like if you have like a skeleton, like a cartoon character, you try to represent the position of the cartoon character. It's just a bunch of angles, and apparently you can represent this as a sort of 1D series. Never thought of that. 2D is really the meat of where convolutional neural networks are used. It's images. Or if you want to make your life a little more complicated, an audio after Fourier transform, which means we've seen those things. Representative of sound as sort of those color bars that you see, which represent each frequency, how loud it is at each frequency. So that's basically a spectrogram is called. And it's just a visual representation of the sound. So you're cheating because you're really transforming the sound into an image, and you're back into the image now. 3D, so things like actual 3D visualization, so a CAT scan, like you get not pixels but voxels, like little cubes in space. And it's a cube you can year big by year big by year big. Or a video, which is an image, an image, an image, an image, an image. And you can think of this as a 3D object as well. So you can use convolutional network over all this. The truth is you can use it on more than that. A number of people, but Jan has been very good with this, is trying it on text as well. So people have done all sort of crazy things with text, where they take, the only problem is you've got to take it sort of fixed size segments, and then you use convolutional networks, and you can make them do all sort of interesting things. Now, just for the sake of this presentation, mostly images. I'm going to have mostly images as representation and the way to think about them. All right, from the book, this is what a 2D convolution looks like. On the top left, you have your image. So the different pixels are represented by A, B, C, D, and so on. And of course, it will be, 256 by 256 on your typical, or 224 rather, by on your typical ImageNet thing. More of this, and some new stuff. And then here you've got a kernel. So in this case, it will be a 2 by 2 kernel, which is a strange choice. Nobody does that anymore. Everybody loves odd numbers for kernels. Why? Because there is a center and a round. That's the main reason. But 2 by 2 kernel, and what you do is you multiply. So you take a 2 by 2 region of the image, and you do A times W plus B times X plus E times Y plus F times Z. Okay? Something like that. There you go. And that gives you the value for the neuron, and for the activation at the next layer. And then you move, let's say by one position to the left, and they give you this one, and then another one, this one, and you go below, and so on. So you've basically taken this set of weights, multiply them by the pixels and by the signal at the lower level, and you get this new set of values. Does that feel intuitive to you? Or should I think it's horrible.
How are the weights determined?
So the weights, okay, so in the old days, people would fix have armies of grad students come up with the right filters and basically find the right weights to do this kind of thing. These days the weights are learned, so we're going to get through that. Right? So they start random, and then depending on what's in your images, they set on some things, so I have plenty of visualization for you. So what I mean by, it's not intuitive. I don't fully understand what exactly is taking place, and I want something more visual. At least it's me, I'm more visual. So I try to, first, this is the slightly wrong, but intuitive enough thing. What the heck is a convolution? A convolution is like running a signal through a filter. Right? The convolution itself, the kernel is the filter. So think of them as funny sunglasses. This is my filter. It's got a slit, and it only wants to match things that look like that. So if I take an image like this and run it through this, pretty much everything goes through. I get a very strong signal on the output. If I take an image that really doesn't look like this, sort of a question mark kind of thing, the only place it's going to go through is a little thing here. So now I've got a very weak signal. It's a poor match. Right? So the question, the kernel is trying to say, do you look like me? Okay, how close do you look like what I am? So this is sort of to me the kindergarten explanation of what a convolution is. And then the geometric explanation of what is taking place is here. So let's say it's an image. We start with the image. Right? So what we have is typically 3 layers, RGB, 3 layers of colors, and I'm picking a 5 by 5 kernel. So this is just a teeny fraction of my image. The pixels are coming in, and I'm going to compute one value by removing this filter. Right? So there'll be weights at the end of each of those, 3 pixels, and so on. There's like 75 different values coming in. Right? 5 times 5, 25 times 3 colors, and then 1 for the bias, just to be fun, 76. So those things will compute this one value. Typically, after that, there is almost always, there is a nonlinearity. So typically, it's a ReLU, right? So rectifier linear unit, to basically make a choice. Everybody knows what a rectifying linear unit is? Yes, okay. So you make a choice, and then you shift this by one pixel somewhere, and you get another position which will create another one. So it's actually going to look like this. Right, so now we're looking from above. The image is there. And my 5x5 kernel is the red square. I do this computation by taking all the layers below, and it's going to produce this one guy. Here, this value. Then I'm going to move it, and there's this thing called a stride, and you can choose. It can be 1, it can be more. So if it's more, that is going to be smaller, right? So there are a number of parameters like this that they can change depending on what you try to achieve. Yeah, so you get a stride. So let's say it's 1 by 1, which means you just move from every pixel, but you could also have 2 by 2, which means you move 2 pixels in that direction, and then when you move down, you go 2 pixels as well. So this thing will shrink roughly by a factor of 2. Okay? There's also something interesting happening on the edge. So if you insist that your kernel sort of fit perfectly in your image, you're going to lose a little bit at the edge. Or you can add some extra 1 or 2 rows in order to get, in order to not lose any pixel. So the question is, can you center this 5x5 on this last pixel? And to do this, you need 2 rows, and you can choose what you put there. It can be a 0, it can be sort of a repeat of this, or mirror image of this. So there are various options for that. Most modern libraries will give you the option, just a matter of putting the right option. And that's pretty much everything that happens there. And the end result is you go from those layers to this one layer above. You create a one layer of activation, which is the result of all those windows of pixels running through the filter. So in places where the value here is high means those filters are happy that detected something they like. Okay, now whether those filters, where they come from, we'll get there in a moment. Now just for the sake of being complete, there's no reason to just create one neuron. So the exact same pixel can be sent to multiple layers of neuron, which are independent. Right? So then you get to learn more stuff. So you get to learn more filters at the same time, at those different through those different layers. And that's a very classic way. I'll show you a real example of convnets. So in this case, we start from 3 colors, and then the next layer will have 7, just because I said so. Right? There's nothing magical there. Typically, you get more and more layers, and the images shrink. And I'll take you through that. Okay? So, and those layers have different weights. Now, there's something that I forgot, previous slide. And I promise you that a few slides back, shared weights. So if this network worked like we used to with fully connected networks, every one of those pixels will have its own set of weights. Right, so remember the sort of K weights, 25 weights kind of thing, times 3 maybe. Yeah, 75 weights. But there will be 75 weights here, 75 weights there, and so on. The thing is, this is going to learn, and there's the interesting little pattern where there's some dark on the side and light next to it. And this guy is going to learn the same thing. That this is an interesting pattern, and they're all going to learn the same thing because probably over 1 million images, that pattern is going to happen often enough for the system to learn that, which is a bit of a waste. So instead, what convnets do is they share the weights. So there's actually a very small amount of weight. There's only, over this entire thing, even if this image was, 250,000 points, like typical ImageNet kind of thing, there would only be 75 weights on this layer for this entire thing. So the net result is they learn the presence of certain patterns anywhere in the image, which is really what you want. Right? You want to detect that there is a little circle, or there is an eye-looking thing, or there is a blob of a certain shape somewhere in the image, and you don't want to relearn it 20 million times. So this is called the weight sharing, and that's a big feature of ConvNet, and make them even more efficient because you have fewer weights, and it makes them much more powerful because they learn independently of where those things are. Now, when you have multiple layers like here, then each gets its own set of weights. Right, so each get another chance of learning something else, but again, what they learn is going to be true across the whole image. Okay, so when we put it all together, that's what we get. We get some input layers. If it was the first layer like I drew, it was 3 because of the 3 colors, but then after that, it's whatever you want. Let's say 4. And at the end, you have an image. In this case, because of zero padding, which by the way I totally screwed up, there should be 2 layers of padding for this to be true. And that image is the same size. And arbitrarily, I decided 7 layers would be good. Then the process repeats. Almost. Almost. So just one observation, I'll show you why the almost. As you add those layers, actually this should be somewhere else, but oh well. As you add those layers, this image, okay, this slide should be somewhere else. I'll come back. I'll come back to that slide. Just swap it. So this was the convolutional layer. So convolutional networks are made of several layers. One is the convolutional layer, which we have just seen. The other one is typically this. It's called a pooling layer. And the purpose is to take all this information that you got. Right? So let's say we analyze the image and we have all those filters and we put an image, they're going to get more or less excited, so it's going to be more dark or bright. Right? You get a value out of them. And the question is, when you start, you've got on the order of maybe 1 million of those. That's too many, right? At the very end, you would like to have few of those things that give you information about the whole image. So you have to take that information and concentrate it, squeeze it. So this is what those pooling layers do. They take, let's say, a 2 by 2 square. Of course, it can be anything by anything you want. They take a 2 by 2 square and they compute an operation. And the classic operation would be something like max. So they take the maximum value out of those 4 and preserve it. Or you can compute an average, and there are a number of other functions that are basically the same kind of flavor. Right? So they do some sort of summary of what's in that square, and they produce that. And then you can have, again, the stride. So you can either have a stride of 2, in which case the image will shrink by a factor of 4, or not, it will shrink less or not at all. Yeah?
In case of max, how are you going to optimize the weights? If you optimize by gradient descent, you need gradient, but max is, I don't know how you would write the gradient there. And,
so, yes. And I don't know the answer off the top of my head, but people have figured out the trick. Yeah.
So in that case, you would only go back to see which one was selected. You'd only update the gradient for the particular weight that was selected, and the rest would remain unchanged.
like argmax.
Yeah.
Right. You don't. Yeah. That's true.
Rather than 4, 1 would be max, and that's the guy that gets that.
So you keep the track of which.
Yep.
Yeah. Remember which one. Correct.
So is there any implementation? So here we just took the max or we took the average, but is there a way of doing this? Is just I'm just running off the top of my head of having a weight that chooses which one was the most which one was the most interesting square to keep?
Not that I know of. I mean,
I haven't read anything about that either.
No,
so
I don't know of anything that looks like that. It's this is typically a layer that's famous for being not learning. Right. So this is a very mechanical layer. There's no well, I guess max is some sort of non-linearity. You make a choice. You choose the max one or the average, but there's no weight in there. There's no learning. The weights are in the convolutional layer. Okay. So the typical use, again, people have done, can do all sorts of things, and you always find a paper that tried a variation, different size of this, different stride. You try to not shrink the image. You try to shrink the image quickly. Typically, it's used to shrink the image more or less, let's say by a factor of 2 linearly, so 4 in number of pixels. So you start from an image that is, let's say, 256 by 256, and 128, and 64, and in a few layers you're down to a very small image, and at the same time you add more layers. You start from 3 layers of pixels, and then you have, quarter image with quite a few layers in parallel, and then it just keeps going like this. So the pyramid sort of gets, smaller and smaller at the top, and sort of every floor is taller and taller. So I'll show you images of this. An interesting property of max pooling. So 2 things. Because of that,
I think
One little question.
Yeah.
Has anyone switched back and forth between, based on the previous question, max and average, for example?
it's at the point where everybody says max pooling. So I think max is...
It's been converged on?
Yeah, it seems to be the easiest one. It's not clear that the average actually tells you anything. I'm sure there's somebody somewhere else published a paper, comparing in details. Yeah, you see.
So if you have, say, so you spoke about having multiple filters and like the number of filters grew, right?
Mm-hmm.
And you only apply like your kernel to a specific filter. So what do you do for all of the other ones? You sum them up together for a particular value?
I'm sorry, for which operation?
So if you could go back a slide. So like say you have like an RGB channel. Yeah. So out here, so it's 5 by 5 by 3, right?
Mm-hmm.
So what would happen to like, say this went over an image, at its lowest level it's a 5 by 5 matrix multiplication on an image, right? So is it like one filter for every color?
No, the filter would combine the 3 colors. It would have access to the 3. Right.
In principle, you could have filters that would learn to follow a given
exactly.
color.
So the filters will be learned. Right?
Yeah.
That's the thing. So the filters are the weights will be learned by going in this end. So each of those, symbolizes a neuron, and it gets 5 by 5 by 3 inputs. So it's got 5 by 5 by 3 plus 1 weights, and it will learn that, and then it will produce this one pixel on the next, one neuron on the next layer, and this is another neuron on, I guess I'm using layers a little loosely. This would be, those 7 would be, depth of 7 would be the next layer.
Okay.
They're just independent. You say, I want to learn more than just one filter, so I want all those layers independently.
Okay.
There's just more chances to learn.
Okay.
If that was your question.
Thank you for that.
Okay. So the max pooling, to go back to this, is this interesting, the combination of the convolutional layer and the max pooling typically will shrink the image. But if you look back, so imagine that you have a few layers, and I'm sorry I don't have a good representation of this other than that. You have a couple of layers that do this. You see that pixel, if it was let's say a 3 by 3, whatever, represent, kernel, would be affected by those 3, and then those 3 would actually be affected by those 5. So what makes up one of those points on a high layer is a bigger and bigger fraction of the image as you go down, right? So this is another interesting property, which is even if your kernel is small, at each layer you learn a little bit from a little neighborhood underneath you, but because that layer did the same thing below and the same one below and so on, with enough layers, you actually learn from the entire image. Right? So somewhere you was learned that there was a little corner, another little corner, and then those 2 corners came together, and then those things came together with something else, and then that's how you recognize a person. So we'll go through more examples of that. Okay, so the max pooling, I think that's all there was to say. So this is it's pretty bad. So I'm not going to do it, but if you look at your typical ComNet, there's a convolution layer, there's non-linearity, there's a pooling layer. The question is, how many layers are there? So it depends. So people play games, right? Either this is 3 layers or this is 1 layer. And so when people say my ComNet is 50 layers, the question is, what do you mean by a layer? because it can make a big difference. It's just a point of semantic, I guess. It's not a very big deal, but it's in the book. It was a slide. I think it's worth mentioning that there's not like an easy answer. Like, what do you mean by layer? Often people don't count the nonlinearity as a separate layer. It's sort of, going into this, so that would make two. And typically people talk about convolutional layer, max pooling, convolutional layer, max pooling, so that would be another way of counting. Okay, just terminology. Okay, another interesting property of the pooling is it actually helps. So the convolution is pretty much invariant to translation, again, except around what happens around the edges, right? But if you move an image a little bit, the activations at the end will be, in the next layer will be the same, except they'll be shifted by the same amount, give or take. The image shrinks, but anyway, you get the idea. Max pooling is the same property, right? So as you shrink your image to a max pooling layer, shifting the image doesn't really change what happens, which is a desirable property because, again, when you take a photo, you don't try to have things land on factor of power of 2 pixels or something like this. It doesn't matter whether things land. You still want to know if there's a cat or a person in the picture. So that's why it's a good property. Both layers have that property that's important. Here's a great little story. Those networks are invariant to translation, not rotation. And I learned that the hard way. So I have my little stupid story. So a few months ago, I was working on a little network just for fun. I was trying to basically, I have 3 kids, so I have a gazillion family photos, especially from the old days when camera did not rotate automatically, and so I have a lot of photos with the kids like this. And I was, wanted to run something over them to detect the ones that I should fix, or fix them automatically. So here I am, rolling up my sleeves, Keras, model, lots of training data, and I get my model and it's working pretty good. And then I try to test it, and I make the assumption that, well, if I train my model, and if I put a picture like this, and it says, rotate it like this, then obviously if I put it like this, it will tell me it's good. Right? Then if I put it like this, it would say, well, turn it that way. Of course it would say that. Except it doesn't. Because there's nothing in there that says that by turning 90 degrees, the thing would automatically, give you the exact same answers modulo this 90-degree rotation. It's totally not true. So then I turn that into a positive. I said, okay, so now I've got 4 models and I can do an ensemble. So I took my photos and I fed them to the model 4 times, right, with the 4 different rotation, and I got 4 distribution which I added, and I got 5% increase in precision. So there you go. I was very happy. If you want your ComNet to be invariant to rotation, you have to do something like this, where you create essentially a different type of pooling unit where you feed the different rotation, let's say, and the system will learn that rotation doesn't matter. Right? But you have to explicitly do it. This doesn't happen naturally. So that's the lesson. Translation happens naturally. It's in the math behind the convolutional layer and the max pooling layer, and it's going to work. But you don't have to worry about, oh my god, if the cat was a little too much to the left, that's why it failed. No, not true. But for rotation, you have to explicitly do something. All right, where are we? So now I'm going to show you a few ComNets, sort of classic. So this is the teeny bit of history here. ComNet were probably mentioned for the first time by this Japanese researcher in 1980. And so Jan LeCun, the same guy that I mentioned, whose photo I used initially, in the mid to late 90s was working at Bell Labs, and I think even started before that, and created various, very small for the time, convolutional neural networks. They were supposed to do about as simple as you can get, work on teeny images, right, 32 by 32, to do handwriting recognition. And in fact, it worked, and the system was commercialized and was reading like a good fraction of all the checks in the US. So they would be, read by issue using this kind of system, which is pretty impressive for the time when you consider. So there was a 32 by 32 image, and then it would go through, whatever, 28 by 28 feature map. So there was some convolutional layer, and then you can see 28 divided by 2, 14 divided by 2, probably 10, so not quite, who knows. So anyway, they had like 4 layers, and then at the end they took all those activations and threw them into a few fully connected layers, and the last thing was a softmax, I guess, maybe, that's what we call it, to give you, which number between 0 and 9 was supposed to be represented. That's funny because they draw an A, but 10 output means it's going to be numbers. So anyway, you get the idea. It was teeny for the time, but it was very impressive. I mean, it was teeny for now, but impressive for then, and actually worked. And they probably tried simpler things before, and that didn't work. Okay, then every year there's this ImageNet competition. Anybody has not heard of ImageNet? Everybody has heard of ImageNet. Okay, I'll have to explain. So those are some of the winners, and they're also the networks that have sort of stuck in the sense that they seem to be pretty good, and they're available. Those are things you can download. They've been pre-trained and so on. So sort of bread and butter if you want to do some image classification task is you download one of them and you do a few tweaks, and you're off and running in no time. So this is VGG. So this is the Oxford group did that, and what you have is a convolution layer, another convolution layer, and a max pooling layer on 64. So those are the images are 224 by 224, and you got each of these as 64 in parallel. So lots of signals. Then next layer, shrink by 2, 112 by 112, so 4 in terms of pixels, and double the depth of those things. So now you've got even more layers to learn, but on smaller images. They're not images anymore, they're activations, but smaller. And then do it again, and again, and again. Now at this point, the image is teeny. You've got a lot of different signals, and all the bits on the last one are thrown together onto a fully connected layer, another fully connected layer, and a softmax. And now you can recognize 1,000 classes of objects, which was the purpose of those things, including breeds of dogs that you cannot tell apart, but the system can. Right. So that was the kind of game that ImageNet competition that you do. So this is a classic. The only downside is pretty big. It's got a lot of weights. It's a pretty heavy network. This is another one, just for the sake of, when you want to make things complicated, you can. So people at Google, somebody named, whose last name is Le, invented that. And so it's based on those little groupings here that have 5 by 5, 3 by 3, and 1 by 1 convolution. And then they put all those things together, concatenate them, and then they do it again and again. And it's complicated, and don't ask me, because some of the stuff I don't know why. Like the different softmax, I'm not sure. What's funny here is the 1 by 1 convolution. So anybody wants to take a guess why 1 by 1 convolution is interesting?
Reduce depth.
Yeah, because it does, from an image point of view, it does nothing, right? You take one pixel and you spit out a pixel, okay? But actually, you take a stack of pixels and you spit out a pixel. So you actually mix depth-wise, and so you can reduce the depth, and you can have more if you want. But it's basically another chance of learning without doing anything interesting in the image sense. You're not learning from the neighborhood; you're learning from the depth. That's why they're interesting. So those are 1 by 1 things as well. It was, I believe, smaller. And this is my favorite. This is the winner. So this is done by Microsoft Research, if I remember correctly. Interesting architecture. So they went crazy with the depth. This is a picture of the 34 layer one I use usually the 50 layer one, which is smaller and better than the VGG. So it's got fewer weights, a lot fewer weights, and it's pretty fast. So it's really a good go-to network if you need something. And they tried all the way to 1,200 layers in the paper. So there's some crazy paper with, and the 1,200 would overfit on anything. So there's one idea in there which is really interesting. When you have all this depth, basically whatever signal you have at the beginning, so this is where the inputs show up, whatever you have here will get written so many times. Every layer gets to rewrite history, basically. That what you learn here is lost by the time you get there. Which means training can be slow. I mean, there are issues when you have 1,000 layers or even 50. So what they did, they added those bypass, where they take the input, they compute something from the input, but they then mix it back with the input. I think in this case, they just add the two things together. They have to be careful with the size and so on, but that works. Which means that a lot more of the input survives that thing. Just to be a little complicated, some people have argued that this is actually an ensemble of models. Like if you look at it from the end, you've got whatever you learn through the entire stack plus whatever you learn through the entire stack minus 2 plus whatever you learn through the entire stack minus 4 and so on. So that's why so it's good. So this is just arguing for fun. But this works really well. I mean, this is a remarkable network. It's it's pretty easy to train. It is much more. I forgot how many times, but it's at least an order of magnitude lighter than VGG, and it was great. I mean, that's what I used when I was doing my image rotation model. But this thing will happily learn 1,000 classes and do well. Yeah.
And why is it so much faster with so many more parameters compared to VGG?
No, it's got fewer parameters. That's the trick. It's got fewer parameters.
Oh, because there's less layer depth.
No, there's more. There's more depth.
But at each layer, there's less channel depth. Or
Width?
Honestly, I mean, you have to do you have to look at every layer, but I should have done it. So if I ever teach this again, I will do the thing. But it's got a lot fewer weights. That's the trick. And I forgot why. What did VGG must have done something wrong. What was it?
VGG has a lot
A lot of?
Most of the weights are fully.
Yeah, it's the fully connected.
Build up
at
a
the end, I
lot
think.
at the very
Yeah. It's the fully connected that
Those
kill
fully
you. Because
connected
fully
just
connected on 4,000 is pretty, there goes 8 million a pop kind of thing.
half the gigabyte weights right
Yeah.
there.
Yeah. That's why, yeah. So, okay, so that's ResNet.
Question about the image sizes. How big an image size has anyone really worked with?
Because of ImageNet, all those networks so far are 224 by 224, and with the RGB mixed up, and with 3 magic numbers, which are the average on the original ImageNet, which need to be subtracted for the network to work. So you have to do this thing just because we did it last year, because they did it the previous year, because they did it in 2012. You got to do this strange little song and dance. But so that's the reason. Now I know there are networks that do things that work on much larger images. Things that either detect object in images, and the object might be teeny, so you see everything in the image. Or I guess network that play with like super resolution, where you so they're not exactly the same shape, but you take an image and you learn a high resolution version of it. So you take basically a low res image and produce a high res image. So those tend to produce things that are more like 4K by 4K. Maybe I'm wrong, but something like that. The 224, so it's classic just because all those classic networks do this.
Well, I'm wondering what the ramp up in hardware and time would be to say double that. Call it 600 by 600. If anyone knows.
Another excellent question. Well, I mean,
what's involved.
it wouldn't be. You would just add another layer, and if it's a convolutional layer, it wouldn't be crazy. I mean, it would be. Again, the cost tend to be.
Well, you'd have that much greater width of your layers, right?
But just for one layer.
Ah.
Right. I mean, if you do the max pooling, you could get in one layer you could go from 512 or whatever to 256, right? By 256, you could have a quarter of the image. So, quadrupling the number of pixels would take you one normal convolutional layer.
Mm-hmm.
So it wouldn't be death. I mean, I think people, all the publication and so on, they want to compare to what they did last year, which is why we're stuck with comparing to 2012 forever.
Right. It just seems if it was that trivial, you'd hear a little bit more about it. But
no, I think people privately do it.
Okay.
I mean, it's like, real application in your business if your image tend to be bigger or smaller. You just size your thing. It's one number at the beginning, and Keras or TensorFlow, whatever, will take care of sizing things for you. So it's not a huge deal. Yes.
Two questions is I can kind of grasp the idea, with looking at images, but I'm having trouble wrapping my head around what would a time series look like when you throw it in there? What would your input look like, and how would it differ from what you're doing with images?
So they would be 1D convolution, which means instead of having your image, you would think of a line, and you would take that little window of whatever 5 pixels, or and move it across, and that would look for patterns. And so one would detect the thing is going up, another one would learn to detect it's going up then down, that kind of thing.
But also LSTMs would be more applicable in this case.
So that's a different thing, yeah. So yeah, I mean there are for one-dimensional things like text or time series, recurrent neural networks like LSTM tend to be really good at that. They tend but you also have people, especially on Facebook, especially on Yarnacon, who will argue that ConvNet will do at least as well and so on. So it's not impossible to use that. But like I said, the images are really the bread and butter for convolution. You had another question, I'm sorry. You said two.
Thank you. I've been really curious about using neural networks for point estimation. I know we talk a lot about classification, and I was just trying to understand kind of the scale of data that might be involved for trying to do point estimation.
What do you mean by point estimation?
Well, let's say you wanted to forecast hourly data into the future, and you wanted to know, what value.
Oh. So, okay, well, I mean, you would have, maybe I'm going to give the wrong answer, but instead of having a soft max at the end, which decide among, so many classes, you would have just a logistic regression predicting a value. So you'd not put a continuous value, right? So you would predict a certain value. So during your training, you would have that. You would say, for this input, I expect 4.5. For that input, I expect, 17.3. And then the system, the network would then predict those real values. Is that what you're asking? Yeah. So that's everything else will be the same. Just the very last layer will change. Okay. There's a fascinating subject which Ian covers in the book, which I think is really interesting. Is how close is this from what's between our ears? So that's always a fun subject. So okay, so in one sense it's remarkably close. That's not the whole truth, right? So visual system expressed here, eyes, retina, optical nerve, some other routing thing, and then we get into the visual system. Visual system is very creatively named, by layers: V1, V2, V3, V4, 5, I guess, and there's two different trees, and those are layers that literally, you can think of them as convolutional layers. In fact, it's worse than this. People have gone through a microscope and looked at various, mammals and what they were seeing and what the cells look like, and a while back they figured out, I was good enough to get a Nobel Prize, by the way, that there are two, in those layers, especially the V1, the first one, which was the one they studied the most, which is where the signal from the retina shows up. There are two types of cells. One they call simple cells. Those guys really knew how to name things. And simple cells were literally like convolutional cells. They would take the signal from neighboring things and combine them. And then they had complex cells, which were essentially doing a max pooling. They were taking the output of several of those and combining them and saying, something exciting here in this neighborhood. That's all I remember. There was something very exciting there. Right, so that's the max pooling thing. And then you've got basically about 6 layers of this, and by that time, you can tell grammar, which is surprising, but that's how it works. Right. So in that sense, it's reasonably close to what we have in our visual system. But the truth is, and it's not interesting, by the way, it's not enormous. I mean, 5 billion neurons is not a huge number. Now the catch is, what we call a neuron, I mean, in our case, a neuron is a multiply add with some sort of nonlinearity, some sort of choice. Apparently, in our head, it's a little more complicated than this. It's more like an entire city. Okay, so it's not exactly, I mean, I'm not a biologist, but when I talk to people who actually study this, they have a respect for the neurons that we don't seem to have. So it's not just a multiply add. It's a very complicated beast with a lot of things. The second thing is the connectivity. In a classical CommNet, you go one way. You go from the pixel to the high-level signals, and that's it. In our brain, it seems to be much more complicated, so there is feedback. There seems to be something that, after the signals have gone up, something comes back and says, I think the thing in the shadow is a cat. And now those neurons go, oh, it's a cat. I must be the whiskers. Yeah, I'm the whiskers. Things like that are taking place, which don't take place in a normal neural network. And there's also sideways connections, so probably things like, oh, come on, 12 of us have decided that we are part of the, nose of the dog, so you better also say yes. Things like that. There's the various local effects that have no equivalent in CommNets that seem to take place in the brain. So basically, it's superficially, it's the same kind of connectivity, but when you zoom in, it's a much different thing, which I think is always fun. All right, this one I find not so fun, but this is the kind of stuff that the brain seems to learn, and little at the bottom, V1, so kind of edge detection kind of things. And this is where a generation of grad students were enslaved to code for years before CommNets. And when you actually try and do sort of the simplest thing possible, this is the kind of filters that get learned, of kernels that are learned by CommNets. So they look alike. So yes, we have some similarity between the two. It's sort of obvious. I mean, what else would you learn? Right? I mean, if you're at the bottom, right? If you just get your pixels and you get to look at a 3x3 or 5x5 windows, what else could you learn? So it's light and dark, or light, dark, and then light again. That's about it. You can't do much more. Oh, this way, or this way, or you're done. Right? And that's exactly what the thing learns. Okay, the fun part. So whenever I work on CommNets, I have to visualize what the heck is going on, and it's always so hard. Which is why I will never forgive that book for not having enough pictures. Right, so if I were to open the hood of a CommNet and look at it when it's working, what would I see? So there was a great paper written in, I think, 2014, 13, something like that, and I'll show you some images from that book. So here's a very simple example. This is the picture from the book, so here you go. So the idea is the simplest kernel you can imagine. This is a 2x1 kernel that does take this pixel and subtract the 1 to my right. Okay, that's all. You run it over fluffy here, and you get this. So you get edge detection. Right? It's whatever. It is dark when you go from light to dark, and it's light when you go from the opposite. Okay, so this is what a convolution can do for you. But this is a hand-coded convolution. So if you were to give 1,000,000 pictures into something that used gradient descent to learn a bunch of weights, what would it learn? So there's that paper. It's a great paper too. 2013, right? So this was like 2012, if you remember, is the year when ImageNet was won by CommNet, so that's when things just exploded. So this came shortly after that. Somebody had the same question. Let's open the hood and see what's there. So, first layer, guess what? edge detection, more or less, right? We see. And so this is a visualization of the kernels themselves, and this is images from the validation set, or routine segments, that sort of got those guys the most excited. So those images sort of get the maximum activation from the different things. So that means is the following. It's 3 by 3. Those images here, they got this filter very excited. Okay? And it's going to be the same for all the other ones. So this is the bottom layer. You get little edges. This is the next layer. And so the next layer is taking activations of the previous type and combining them. Right? So very quickly you get interesting things. You get, so those are the images that react to this the most. So you get parallel lines, straight lines, or parallel arcs of circles. You get concentric things, so we're now aware of detecting eyes and galaxies and things like that. And then you got some sort of gradients. Don't ask me why that would be exciting, but apparently it is. And some stuff is wrong. But it seems to get that guy very excited. It seems to be the yellow part that it finds interesting. I mean, we don't always understand why something was learned, but it was learned. Right. Okay, the next layer, you get more complex things. You get like honeycomb kind of patterns, you get flowers kind of patterns. Yes, you start seeing faces, blobs that happen to be faces in this case, but there could be other things. You get wheels, again, kind of pattern. Probably the thing doesn't make much of a difference between the face and wheel. It's just in 3 layers, combining very simple things. That's what it gets. And then another couple of layers. This one you definitely on like dog nose and bird feet. And then you finally get like the full thing, like people and dogs and all much more complex things. Right? So a girl with eyes. Legs over there. So you see how those things combine, right? You got little simple patterns at the bottom, then combination of those patterns give you intermediate patterns, and then more, and then you can get anywhere. And so, as you can imagine, in maybe 5 to 10 layers, you can basically learn just about anything visually. And somebody throws 1,000 layers, then you can literally learn anything. I think the current intuition is that what matters in those conv-nets is the number of nonlinearities. It's the number of redo layers. Because that's the more you have, the more you're able to learn. That seems to be the thing. With, of course, also the issues of why people create those complicated topologies.
Can you repeat that one more time? What's important is the number of redo layers. Can you repeat that?
Oh, I'm sorry.
Repeat one more time.
Which part?
Number of redo layers.
Oh, yes. So the intuition I read a bunch of times is the number of nonlinearities. Right? So you have conv-net, you have max pooling, and so on. The learning is really the number of nonlinearities because those are all choices that are made. So intuitively, that's what seems to matter. And having more of them gives you more, expressive power, learning power. And this was my last slide. How am I doing timing-wise?
Perfect. We have tons of time for questions.
We'll take questions. And then I'll take a random person in the audience to answer the question, because I don't know. Yes?
Do you have any intuition of instabilities? I mean, you probably saw the famous image, probably Jan's, some like Jan's Goodfellow paper when he shows thunder plus a little bit of a noise and it becomes a gibbon or a worm.
Yeah, so this is I'm not an expert in this, I've never played with that. But so the idea is you can take an image and by adding just the right noise, so a little bit of, it's almost invisible to the eye, right? So you take an image, you add this noise, it is the same. And now the thing was saying, this is a panda, and now it's going to say it's an ostrich or something like that. Completely different. You say that this network has gone nuts. Right. So it's called adversarial training, if I remember correctly. So I think the trick there is you need to have access to the network. You need to know exactly how the network works to do that. And I mean, my understanding is that it's just a matter of, that noise. How can I explain it? Help. That noise will just give a bunch of little kicks in the right direction to all the different layers, and eventually will overwhelm the real signal. Right? That's the best way I can explain it, but I can't really take. I mean, you have to go through the math to see how you can cheat. If I remember correctly, Andrei Karpathy has a great blog on that. It's probably him, or was it? There was a reasonably understandable explanation of how this can work, but I read that so long ago. All I remember is, okay, let me rewind. This matters because the question is, can I take an image and show it to the security system, which I know as, automatic face detection, and it will say, I don't know, famous person walking by. And the image was just, me with a little bit of distortion. Right, so that's the kind of thing. So people are afraid that, we'll be able to cheat any visual recognition system. And I'm not an expert, but I know that it keeps the security people busy. And so it's an active area of research. I think that in order to make those things work, I don't think you can have a universal distortion, like take an image that, if you apply this noise, then any network will now say it's an ostrich, even though it's a panda. I don't think that's the case. I think the noise has to depend heavily on, has to be tuned exactly for that network. That's all I know. Anybody knows more about this than me? Because I'm sure that's easy.
So actually, I was one of the authors of the first paper on this, San Christian, and so actually one of the surprising things was that if you to figure out the distortion for a network, then it typically, statistically, it gets also misclassified by other networks, and not necessarily networks, but any models basically.
Any.
Yeah. So it's kind of the top, even if trained on a different data set.
Okay, so that's totally scary.
So it's so these distortions are surprisingly robust to this kind of, so even the different architecture, different data set.
Okay, so that's totally scary. Which is great.
But, so that's one of the things that is still not very well known why it's the case. So it's not very well explained.
And is there a way to train harder in order to protect against that? Could you have a training procedure that makes a network resistant to that?
Yeah, there has been a lot of papers since then. People tried various. They with limited success. So there's always some improvement, but it's not fully solved yet. So it's not. There is no clear way of saying that that's the best way to train the network for robustness. So it's a lot of ways, and each of them kind of works, but not very well.
Right.
So that Google/Kaggle just released 3 competitions. One like to do adversarial training, one to try and predict it.
That's cool.
Yes. So you can compete either in cheating the network or in making the network more robust. So it will be interesting to see what.
But what's your intuition? Will we find ways of training that protect against this? Because it clearly doesn't work on people, right?
I mean, I don't have a good intuition. I don't trust my intuition anyway.
Any more questions for Louis?
Sorry, what did you mention? Odd size filters as opposed to?
Oh, just so I think initially for whatever implementation reason, people used to like powers of 2 kernels, and then an outside filter is easier to visualize because there is a center and then there is, you know, the border around it. So it's this and then everything at distance 1 or 2 or 3 from it. So today, if you look at all the networks, they tend to have outside filters. I think it's literally for that reason. It's more elegant visually to have a center and a nice little region around it. So I don't think there's anything magical. I mean, you know, I think 2x2 kernels would work fine. Yeah.
What's your favorite architecture right now? Is it like a bazillion layers or something
Oh.
more elegant?
Well, I mean, if you want to, I mean, right now I'm not doing any research on convnets, so it would be favorite in the sense of, you know, if you ask me to do a classifier by tomorrow night, or maybe even less, you know, and I've got some data here and chop chop, you know, get it done, I would use ResNet because it is smaller than the previous ones and it's better and sort of, you know, it's got a couple of points improvement over the VGG, for example. So it's probably a very nice sweet spot. People have tried various things now, so there are like very small networks that still do okay. Like, you know, there's something called SqueezeNet, DarkNet. There are various things that, you know, tend to be very small, so you can put them on a little system, and they still have acceptable performance. So there are other dimensions in terms of being best. Oh, that's what I need to show. So another little story just for fun. So I brought those two guys here as support for the French accent, because in case we need more French accent, I've got that. They're interns. They're staying with the interns not at AirBnB, even though they show up a little too often. The food is good, but at a French company, and totally unrelated to their day job, they were given a little project, which is to build a self-driving car. And I'm going to show you what a teeny convnet can do when you throw it at a couple of people who are motivated. So this little car has a little teeny camera and a Raspberry Pi, and then talks to a model, which now is small enough that it could actually run on a Raspberry Pi. I just haven't had the time to do it. But so it's running on the laptop, but you know, nobody's driving. Right. So it's actually working. And
what's the sensor?
It's a camera. It's a little guys. What is the? And then it's gonna screw up because it's basically a trap. And it doesn't have the radius. It could survive, except it doesn't have the radius to, you know, to survive the garbage can. So, what kind of camera is this?
It's a Pi camera,
Okay.
a Raspberry Pi camera.
Okay.
With a wide angle.
Right. And then you chop it, so it's actually, what is it like?
70 by 250 image.
Right. And then it's a very small convnet. And that's it. And then the output is straight, left, or right. So it's a 3 or 5. Okay, 5, you know, straight, a little bit left, a lot left, a little bit right, a lot right. That's it. That's all you get. And it can do that. So, you know, convnets for fun.
And the laptop has the gas pedal?
And no, actually, the gas pedal was initially yes, but then the gas pedal was put in there, and we should train it again with the gas pedal. But the gas pedal was just automated, as in if you go straight, go fast. If you turn, slow down. Okay. So you have time to think.
What is the training set that's used for this?
So initially, man, real life experience here. I had a ton of fun working with those guys. So initially, it was, you know, somebody drove the car with the remote control, because that's what it is initially, and recorded all the frames, and that became the training set. And it sucked, and it sucked, and it sucked, and it sucked, and it sucked. And then one night I said, enough! I've been telling you to generate images for 2 months. So we're going to just generate images. So literally, right? So they took started with pictures of the asphalt, and then added some pictures, some lines, and every possible combination with some noise in there. And you know, the line can be straight, it can be wide or not as wide. The car can be in the middle or not. and it can be straight or turning, and every time you can predict very easily what the answer should be, and they just generate like what, 1 million of those, and that was a training set. So, and now I understand why, you know, let's say, anybody from Tesla here before I say something stupid? No, okay. So I understand why Tesla has a big simulator program, because you can generate much more easily things that you will never see in real life, but you're afraid of. So that's eventually how. And once we generate those things, and we shrunk the ConvNet enough, that's the other funny thing. We start from a big ConvNet, and it's like, this thing will not even converge. It was just too big, not enough images. And then we just shrunk it, and poof, done. This thing was driving. So that was a lot of fun. Any other question? Yes. Okay. Okay. From the back, and then we'll go front. Go ahead.
Oh, it just about this case. Like, doesn't it make sense to put control after you saw the image, like a few seconds after? I mean, it seems like it makes more sense if you install the camera in front of it, right? You need to turn it like a few seconds after you saw the picture, right?
So one of the big issues they had was latency in the thing, and it was impossible to drive. I mean, so you really want. I mean, this model is very simple, right? It's a ConvNet, and it looks at one picture and decides what to do with the steering wheel. So it needs to react right away. It can't. There is no, you know, the right way to do self-driving cars is much more complicated. But there is no notion of, you know, I'm going to go there, but I'm going to go through those different things. So, you know, my bet is I'm going to wait for another second before I take the. Okay, there's none of that. You do the right thing now. You do the right thing in another 1/10 of a second. And you just keep going every 1/10 of a second until you've the right, you know, until well, you've gone through the whole thing. And it works modulo a few things, like, you know, you get trapped into something like this because it's too simple. It just aims for the middle. And then when you get there, it's like, oh my god, I've got to fix it, then it doesn't have the space. So we've got a longer video. They actually won at a meetup on Saturday. So the thing went through a much longer track, and but no, you don't want to delay. You really want, for this kind of simplistic stuff, you have to do it like right there. You guys are going to release your stuff, right? You're going to release this thing on GitHub? Put it on GitHub? Yeah, so that'll be fun to catch. There was a question here.
What's the size of the network?
Okay.
In terms of parameters, 5,000 parameters.
It's really small.
Yeah. Yeah, I mean, it's a color image, which is, it's about a 250,000 points, right? But then, and it's only 3 layers, right? It's 3, you know, convolution, max pooling, convolution, max pooling, and that's it. And then a fully connected at the end, or 2. 1, 2. No, 1 and then a max, and then a softmax. Yeah, I'm sorry.
All right. Super quick question. If I took a black board and put 2 strips of tape on it and was just dragging it behind me, would it follow me?
Probably. Yeah, probably.
Right? No, but just listening to the training set, it would, right?
Yeah.
Because it would just constantly, it would scan the image,
Yes.
it would see that, it would go straight, it would
Yes.
scan the image, it would see, it would
It
go
would
straight.
totally do
And I
that.
could, like, have
You know, I have a great example of this.
yeah, right? Yeah, because you just...
A few years ago, I bought one of the early Parrot drones, and it had this interesting feature where it would, you know, stay in place by having a very low-res camera looking down. And, well, no, this is better than this. So what I noticed was, at one point, it was, you know, for fun, and it was not quite dark, but it was getting, you know, the sun was down, and I was doing this in a big driveway, and one of my kids was there, and I was hovering right above his head, and then he starts walking, and the thing follows it, and I'm not doing anything. What's going on? It's like, okay, totally featureless gray stuff where there's one funny object that moves. I must be drifting. And this thing was following it, so that's exactly the same thing as what you have. It is, you know, what you know, detect. Yeah, it would certainly follow the 2 lines. Yeah, it's trained for that. In fact, the image was clipped to not be distracted by, you know, the flower pots and the cats and so on. It was like, Look down in front of you, a couple of feet, that's enough. That's all you need. Yeah.
So I had two questions. One was specific to like conjoint implementation.
Yes.
How would backpropagation change with respect to like convolutional neural nets, if at all?
So it doesn't, as far as I know. It's it works really well. I mean, think of it as a subset of fully connected. So everything is nicely differentiable, and you can do it. And
what is the summation involved? You're summing over all the.
So the thing I was going to say is, unless you are, and I don't know how many of you in this room, working on the next version of something like TensorFlow, it will do it for you. Right, so that's the answer. So I try to not go into those details because you can really spend days and days through those nice, tensor operations, and unless you're going to really do something with it, it's sort of an abstract exercise. But we have a specialist here.
I mean, you have a weight sharing, so basically the contribution gets summed up to all the input windows that contribute to it. So you're simply summing. If you do the math, you're taking the derivatives. You take the sum over all the windows that contribute to it.
Okay.
So it doesn't change anything.
Cool. Okay, sweet. The second question I had was, if like you had to build something to choose which path to take in this thing, how would you do that with this particular example?
You mean how?
Like if you had like a fork in the road, how would it choose which one it has to go to?
Oh, it depends what the training set would teach it. Right? If you always took left, it would always take left. I mean, literally, right? It doesn't have a GPS, it doesn't have a destination. That's the difference between a toy thing. But you could train it with, like a sign that says this way or that way and learn that. And as long as it's in the training set, it will learn it. In fact, we should do that. Yeah.
I'm interested, and there's like your shameless plug about your hiring. I'm just interested.
Oh, was there such a slide? Oh, gee, I don't remember.
Yeah, I don't know.
I thought that was not allowed. You mean this slide that doesn't exist? Yeah. Tell me.
Yeah. So regarding the slide that doesn't exist,
Let's make it bigger.
I'm just wondering what kinds of positions are you looking for? What kind of research is an AI lab at Airbnb?
Can I put that in 1 minute plug? So I joined Airbnb 2 months ago to create the lab, and I have right now there's 4 of us, internal people, and the only directive I have is be ambitious. So, what kind of position? Mostly people who practice deep learning kind of things. A few researchers wouldn't be bad. What I mean by researchers is people who really are super deep in one domain. Right? So we already have one like that. Somebody who really knows a lot about NLP and all the latest model and spends half of his days reading the latest papers. So having this in a few domains would be good. But the majority would be people who would work on cool models that help the company. We have a ton of data, obviously. It's a happy product. It's one thing, I've worked in areas like, advertising. It's not happy. You bug people, basically. But then, like, a product like this is happy. So I like the idea of, making better tools, better suggestions, things like that, better matching of, there's a lot of cool stuff that you can do, and we really have all this data. I mean, there's nothing hidden. We know everything about those houses and the people who go there and the people who have them, and so there's a lot of fun. And there's also a company with a good data culture. So there's a big data science group, and I'm trying to do the more advanced machine learning, like really advanced. And so that's the thing. So I'm dead serious. I mean, write to me, and I'll respond to you guys.
Any positions for remote workers? Or you want them all right there?
Everything can be discussed. How remote? Vancouver. It's stuck. Honestly, anybody who's interested or knows somebody who's interested, shameless plug, please write to me. It's not too hard to find. And otherwise, you can ask if you lose it. You can ask Elena, and she'll tell you. Okay. Any more questions? Fun question? Yes.
That was regarding the pooling layer.
Yes.
I guess when you pool, you get a little bit of invariance to like small invariance.
Yes. Yes.
But you also do
So, yeah, I think it's safe. Yes, they are. I think there's even something in the book that shows you that if you, if you, okay, let me try again. If you only have convolutional layers, and you don't use max pooling, but you do what it takes to shrink the image, like to shrink the thing, it will have the same effect. So you don't necessarily need the max pooling. The filters will do it for you. So let's say if you use a bigger stride for the convolution, then it will shrink naturally. If you don't, use the padding around the edges, it will also shrink. So you can do a number of things to shrink it, and I think there's a mention of that in the book. I mean, it's a safe bet to say, what I'm describing is sort of the standard convolution networks, but change anything and somebody has tried it, and there could be reasons. So, yeah, there's the pooling. Just about everything has been tried. So something I didn't mention is the weight sharing. Right? So the idea that the weights are just attached to that one, to the kernel, and they don't really belong to any part of the image. They belong to the entire image. So people usually do this, except where they don't. So, and where they don't, what they learn is that, the typical example, and it's in the book, is, I'm going to feed my network a cropped, scaled picture of a face. So I know that here I would expect eyes, and here I would expect a mouth, and here I would expect ears. So I want to learn those features super precisely in those locations. I'm not interested in, finding an ear here and an eye there. Not good. So, you can imagine some corner case where you want to cheat and, do it differently. So just about everything has been tried, and more coming all the time. Yeah.
Is there a systematic way to do data augmentation? We were talking before about rotating the text characters to give you higher accuracy. Is there a way to attack that problem, with different kinds of symmetries, reflection?
Yeah. So I mean, when you don't have enough example, yeah, that's the classical thing. Is you do some sort of, you can change the colors a little bit, you can zoom, you can crop, you can rotate a little bit, you can mirror, right? So for most, if you're into pictures of cats, real life stuff, then it's okay to do that. Be careful with too much rotation, so a little bit. But if you take a bed and you do this, it's to learn probably, right? So it's gonna be confusing when you try to recognize bedrooms.
So it's very situational.
Yeah, so I think it depends.
So
but yeah,
dropout also is another more generic way.
Which one?
Dropouts. We can set some values to arbitrarily zero inside,
inside
the network.
But dropout is for regularization. I mean, it's asking about getting more data.
Oh, it's a form of data augmentation.
Oh, I see what you mean. Okay.
Yeah,
that's an interesting way. Yeah. So this is really not.
I was specifically talking about symmetries.
Right, symmetries and rotation and so on. So yeah, I think there are, if I remember correct, even I think Keras will happily help you do that easily. I haven't used it, but yeah. Usually I try to have enough images, so then I don't have that problem. It's great when you have enough images. Nothing a few million images won't fix. More questions? I'm going to give you a chance. Yeah.
I was wondering, are there is ResNet 50, for instance, is that, are there certain architectures that are more easily applied, like transfer learning, than others?
Yeah,
because it seems like the way ResNet 50 is built, by passing information from lower layers to higher layers, would make it maybe harder to apply transfer.
No, I've done transfer learning as well, it's great. I mean, on ResNet 50. When I was playing with this model, the rotation model, I start from a trained network and I retrained the top, and then I retrained a few more layers just for fun. It worked a little bit better, but I kept most of it, and it was fine. I think it's my favorite example, but I have no other proof than I tried PGG, and this one was so much smaller and faster and higher quality. Okay, was not too but I'm sure that depending on your use, right? So like I was mentioning, some smaller networks have different characteristics. If you need to run them on a teeny Raspberry Pi or an iPhone or something like that. So
we should
Yeah.
probably
Yeah.
do a switch to a second presenter. And thank you so much for the presentation.
You're welcome.
So I guess we're just gonna go straight into it. I'm sure many of you know exactly who Christian Szegedy is. If you don't, let's see. Do you mind giving a little bit of a presentation about what you do and your papers and your research?
Okay, so I worked in computer vision for a few years from 2013. So I published papers on the adversarial examples and designed the inception network, which was winning the ImageNet competition in 2014, and worked on batch normalization, which is a system. So it's a method to accelerate training. So, and right now I'm working science fiction computer vision to deep learning for formal reasoning and software synthesis. So that's my current research topic.
Cool. Sorry, did you say formal reasoning and software synthesis?
Yes, so we have a research group at Google that we have a project that is aimed at theorem proving and software synthesis now. So, I used to work for 3 years on computer vision mostly.
So software synthesis is creating new software?
Yeah. Yeah, so I mean there are different variants. So my main interest in software. Yeah, so there are various angles of this area. So understanding software is one. So reason about software or to create new software. So both of them we are interested in. So we looked into theorem proving for a while, for a year, and so one of the ways to prove things is to create programs that follow a certain that actually generate the proof. So that is one thing that we are looking at. So generate programs that generate the proof for mathematical statements, for example. But we also look into more immediately usable applications, like given input-output pairs for programs, we generate the program. So, but this is very new research. So right now we didn't publish any. So we just started a few months ago on that part.
So neural nets will be replacing, deep learning will be replacing Java programmers soon.
By Java.
Because that's what I do. But for example.
No, I don't think so. We don't want to replace programmers. It's more like, so imagine that like you could have an intern completely for yourself, and he does everything for you. So it's kind of, it would be cool if everybody could have its own personal assistants. So I mean, the idea is that that you tell me an algorithm, you can tell me it in a few sentences, but then it takes me like weeks to implement it and test it and try it out. So how cool would it be if you can, natural language, you tell the machine of what you want, and then it just comes back to you and says, I tried this, and you say, oh, I didn't exactly think that, go back and then. So that's the long-term vision, to turn natural language into code, and you interact with the system in an online manner. So and the idea was originally behind our project is that there is not so much training data for that purpose, but we have a huge amount of training data in mathematical text. So first we start with mathematics to turn mathematical text into formal specification. You can bootstrap it by trying out what the text might mean, and then you try prove it. And then whenever you find something that is correct, then you can go back and reinforce yourself, saying, okay, that was the right thing. And the system could basically read the mathematical literature and develop a natural language understanding that is grounded in real reasoning. So it's a very ambitious idea, and we are far from that. But so we had a few partial. So we're building out building blocks toward that far goal. It's not that we hope that it will be happening in the next year, but we think you can make significant step towards this goal. And that computer vision might play a role in this thing. So for example, you can, for geometry, or if you think about formal reasoning, so humans typically often tend to think in geometric terms, and also it's like, so we have a lot of geometric intuition. So I think that computer vision might play an important role in that. To really see things, not just manipulate formulas. Yes?
So I have a question that kind of like your thought process when you're designing sort of a new network architecture, like for example, Inception. When you're working on the team for Inception, like what's the process in coming up with something that's completely new? Because most of us, like when we're learning and using like TensorFlow, we tend to just take an existing model and then kind of tweak it a little bit. But to come up with something new completely is like sort of a different ballgame. And I'm particularly interested in hearing like how many models fail before you get like the really, really good one. Sort of what's that process like? Like how many models you throw away before you get like the one that gets published into NIBS and it's like everyone's like, whoa, this is so awesome.
So in Inception it was surprisingly small. So the Inception was a proof of concept. So it was a frustration that so I had a project that went on for half a year with some guys. There is a famous paper by Aurora et al. That like some provable prompts for learning deep representations. And we wanted to, based on that paper, we tried to create systems that automatically create network architectures. But we were like, there were a lot of technical issues with it, and then I was thinking, okay, that might not work out at all. So can we test the idea itself before we waste a lot of engineering resources on doing that, and then I designed the network by those principles that I extracted from that paper. And actually the Inception that they worked like third or fourth try. So the first few Inception models were almost the exact same. It was like using a different weight initialization. So it was basically, I hardly did anything. So it was like, it worked like a charm. There was no real. So experimentation involved in that. But at that time, it was most people were like saying it was crazy because that was the time where like so the network by Matt Seiler was the state of the art. It was essentially an LXNet, a bit deeper LXNet, but it was like 10 times less layers and so much shallower and everything. So it's like most people saw that, okay, it cannot work, so that it's possible. So almost everybody was telling me. So it's more like it was a psychological hurdle to overcome, not a technical. It just you had to believe that this was working. It's not that. So most people thought a lot of things that people took for granted was not true anymore, because when you change from sigmoid to ReLU, then all kinds of things just automatically work. But most people didn't accept that these things work. So that's like they said, okay, that might work, but it might be a fluke. And it's at that time in 2013, 2014, most people still believed in the old mindset that deep learning is like hard or something, but it was not hard. So that's I was lucky because I was just far more confident than others. So, yeah.
What was the name of the author or the paper that you were referring to that you said you were inspired by?
Yeah, so it's cited in the paper. It's called Some Provable Bonds for Learning Deep Representations. It's a very good paper. Actually, it's much better than the Inception paper, and it's hardly cited because it's quite theoretical. But I think that's the first paper where people actually prove that you can probably optimally learn deep networks, and it's kind of a breakthrough. But it's completely unrecognized. Even several years after that, most people don't know that paper. I think it's kind of undeserved because it's a very good paper.
More questions?
Any work on automated bug fixing? Like where you look at the history of all the commits and try to infer.
Yeah, that would be one of the applications that that we could look into it. So you know that there is the long-term research vision, and then there are things that keep your project going. You get the support because people find that you're producing useful things. And of course, automated bug finding would be one of the useful cases that you could do with if you can reason about programs. So I think one of the things that so all this reasoning about programs and in general about formulas is super exciting because you like hardly so most machine learning people haven't tried too much in that direction, and most of the people in the formal community don't believe in machine learning. And I think it's so a lot of the static analysis tools that find bugs are just generate much more false positives than true positives, and kind of you are covered with all these useless corner cases that actually don't happen. But I think with machine learning you could actually figure out which bugs are more important and which alarms are really useful to look at. So there are a lot of applications of machine learning to static analysis of programs. I think it's highly underrated. So that I think it will be the next the next revolution of machine learning and applications. So computer vision is definitely now very hot, but I think the future is that you. Yeah.
So typically for images, there's 2D data like text and images. There's a lot more redundant features. So those techniques work, but for discrete data like is there any hope?
Yeah. So I think that one of the things that machine learning opens possibilities that so a lot of formal reasoning, so formal verification and reasoning is done at the syntactic level, they're looking at the syntactic form of statement and they try to manipulate using certain rules, etc. What I really think is that machine learning can do is to look at also the dual side where you actually have a sandbox that it can experiment with. So you can actually gather intuition about how things behave. So for example, if you look at the mathematician of how, so they perform the experiments of mathematicians, that they perform mathematics in an MRI machine. If you look at the brain, the mathematician is doing a lot of sensory motoric manipulations. So it's like putting objects here and there and whatever. So that's what mathematicians do when they think about stuff. They manipulate things, and then when something like that to work out, then they suddenly generalize. Somehow they do experimentation and then introspection, and then look at all those patterns that they recognized, and then they put them into formalism. So typically people don't work on the formal side. So writing down the proof is the last step. You do 99% of the work before you have the formal proof. So I think that's what I would like to see also in the artificial systems, that it's more like figuring out all the important patterns, and then the formalization should be the afterthought, not the main substrate on which you are operating. But right now, it's all the formal reasoning and everything is operating on the abstract substrate, which is really hard. So that's why it's hard to collect intuition. But I think that there is a lot of ways of like exploring the vicinity of the statements, and then collect a lot of interesting patterns and figure that out. And I think this is these are extremely exciting things. So exciting times right now because all this is becoming possible. So, yes.
Can you tell me a bit about the ImageNet result that was just released yesterday? Do you have time to look over them?
Yeah.
Any comments?
Yeah, I was just looking at like a hour ago. Yeah. So it's so I was surprised because like the new results, even the classification result got a bit better, which was like from 2015 to 2016, it was basically stagnating.
So, and there were quite a few really interesting new architectural ideas. I think it's like computer vision is still going strong. So it's maturing, but so it's still interesting to see that you have this continuous improvement even after the time you say, okay, we have like a human performance in a lot of tasks, but you are getting even better than that. So
was the improvement better than the previous year, or?
Yeah, so it's basically classification. It depends. So on how do you say? Because if you say, okay, the error went from 3% to 2%, so is it like is it the accuracy went from 97 to 98%? That looks less less impressive than you say, okay, the error got cut by 30%. So, but I think it's important to look at the error, not just the classification. So it matters a lot that you have like 30% less errors, I think. But so on detection, it was a bit different, so that the improvements are more incremental. But I think that still there is also a significant, like it was the MAP went from 66 to 74 or 73. So that's also a significant improvement in mean average precision. And then actually exactly at that level, when you go from 60-something to 70-something mean average precision, that's a huge gain in quality actually. So it's like it's surprising that you still get these huge gains from year after year in computer vision, which look like it's leveled off, but no, not. It's I'm surprised personally.
Do you think, in some sense, the computer vision community is starting to overfit to ImageNet?
Yeah.
Because it's used so much that the models are now just too much tuned to it.
Yes, that's definitely the case in some sense, yeah. But so ImageNet competition is still an interesting competition because it's like so many teams compete. So therefore, I think it shows something about the overall field. But I'm not very in general because, for example, at Google, nobody. So it's kind of like our MNIST. So ImageNet is Google just released the open source data set for image recognition. So this open images data set, which contains like I think it's 20 million images and much more than 20,000 classes. So definitely I think it's like, so Google didn't even 3-4 years ago didn't care about ImageNet as a benchmark for itself. It cared about a benchmark for in general models and ideas from outside to judge what ideas are interesting when if you read a paper, something, but not. So big companies have a lot of internal data sets that they're growing and they really care about not overfitting too. So we solve real practical problems.
How well do you think we understand generalization in deep learning, and what lines of thinking do you think are most interesting?
Yeah. I think so it's basically we don't understand generalization at all. That's so I think that's so as you know, you're probably referring to this Ackley paper about generalization. So understanding deep learning requires rethinking generalization, and so that raised a lot of interesting points. And so, for example, for who don't know that paper, so one of the results is that if you put random targets, you're training with random labels, for example, from ImageNet, then all the models that we use, they tend to learn those random targets relatively easily, so random classes. So it's like, so the surprising thing about that is not just that, it's the real surprising thing is that if you think the other way around, then you say, okay, but why, if it's so easy to learn the random classes that you assign to images, then why don't models just overfit to whatever they do and memorize everything? And that would mean that they wouldn't generalize at all. But that somehow doesn't happen. And there is no good explanation at all of why it doesn't just memorize the labels if it's so easy to memorize them. And then that paper suggests a few explanations, but I'm not really convinced by any of them. So one of them is that it tries to learn something that has a low gradient norm. Explanations like that, but I kind of find it very. So I'm a very skeptical person. I don't really think it's really understood at this point. So that's an interesting research topic, actually. I think if there would be theoretical advances that would move deep learning much more forward than anything else.
How do you follow the research that's going on? I know there's archive or whatever. There's NIPS. What are the places you look to see the new research?
So yeah, so I definitely look at archive every day, and it's like super fast nowadays, and so that's kind of cool as well. And also friends, whatever people tell me, that people I trust, and it's like people talk around a lot, so these are the two main.
So archive and then people that you know.
Yeah, because I think conferences, by the time these papers at conferences, they are already outdated. The progress in this domain is so crazy that it's not even worth going to conferences, because it's like at the time it's just boring at that point. It's like whatever you see it's like okay, that's already 4 months old. That's too old. Yeah. So yeah, that's what I think is like the biggest fun is lately. This domain is that everything is happening so crazy fast nowadays. So I was a mathematician before, and that it was like I used to publish something. It takes 3 years to go through review. So this is much more fun, much more interactive. Yes?
Could you explain a bit the difference between the inception architecture and the main insights and the VGG or SNet?
Yeah, I already mentioned this, that it was basically as proof of concept for this idea that is. So one of the practical differences, but what it resulted in an inception is still very much ahead of even ResNet and other competitors is that so not necessarily inception itself, but there are a lot of variants like ResNext or exception. And so I think exception is, for example, and ResNext are very good examples of that you factorize convolutions, you get much more efficient solutions even on top of the ResNet idea. So I think it combines very well. So for example, inception is had 8 million parameters, and VGG has 300 million parameters. So it's more than a magnitude less parameters, and it's like a similar quality. So if you really care about computational cost and complexity, then I think inception is still very much ahead of other ideas. It's like, but there have been progress in the domain. So for example, ResNext is a pretty so it's simplified compared to inception, but it's based on the same ideas. So I think yeah. So it's just efficient. So that's important.
Is this efficiency usually useful when how fast you train your model, or mostly?
No, it trains about the same speed, but it can be each evaluation, so can be faster. So it's more important if you deploy a model in production. So for example, Google internally still uses inception so almost every, because when you have to run something, then it matters if it's twice as fast or not. So it's like really, so it's a money. It's like if you run a model on millions, hundreds of millions of images every day, then it's a lot of money to run these networks.
More questions, guys?
Oh, the mobile. So the mobile net is almost the same as exception. So it's kind of it was developed at the same time. So it was a bit earlier, so that's a very good work, and they really try to be, yeah. So that also based on a similar, so taking inception type ideas to more to the extreme of factorizing convolutions cleverly so that you save computation and get better. And yeah, so that's natural progress, and it's a very good work. And I was always telling like Francois as well, like 2 years ago or so, that it's that one should be more aggressive on that path. So simplify things and keep the really good ideas and take them to the extreme. And that's what most recent work has been doing. So convolution factorization is one idea, and the residual is another idea, and both of them combine pretty well. And attention recently is also a big, important idea. So these three main components can big improvements in network architectures nowadays. But maybe next year will be something completely new and added to the mix. I hope so. Yeah.
Well, thank you so much for coming all the way from Southwark. We'll be going to Town Hall, as we always do. It's just a block away for some beer and some snacks. Join if you feel like it. And while we still have our presenters here, feel free to ask some more questions. Thank you, Christian. Thank you, Flui. Thank you.